Okay, I started recording the class, and we'll go to the question. So let me open my email. I think so. In the last class, I asked one of you, I think his name is Janardhan Janeshwaran, to send his simulation file to me in order to check and clarify his doubts. So he had a doubt about the rise and fall time in the CMOS inverter, and he had forwarded his file to me. I think that this was not the updated file, so he forwarded another file to me. Let me quickly download that. And this is the LTSpice file. Oh, I downloaded it earlier. Anyways, I'll just download the updated. Okay, this is the LTSpice simulation file that the student has forwarded and asked about the question about rise time and fall time measurement. So let's look at the parameters. So he's using two transistors, 180 nano, 2 micron. So width is 2 micron, and for the other transistor, 180 nano, 4 micron. Okay, so the question was about rise time, and let's read the question aloud so that everyone is aware of. So he has done a simulation where the rise time was actually for the PMOS side and NMOS side had an issue. So this is the clarifications. I can forward this to you, everyone, but it is you don't need to read the entire email. Just remember that what determines rise and fall time of a CMOS inverter. Okay, so we will simulate this. Let's look at the simulation parameters. Edit simulation current. Instead of 50, I'll just change it to simple 2 milliseconds. Okay. And what else? I think nothing else. Let's run this file, and I'll click here and click here. So this is 4 micron and 2 micron widths for the PMOS and NMOS respectively. So now if you want to measure the rise and the fall time, so for other students who don't know this, so you can always go to view, then view the log, and from here you can find TR as the rise time and TF is the fall time. Okay, and this rise and fall times are automatically measured by the software while considering some suitable points. So I am not sure whether this is 10% to 90%. See, by definition, what is the rise time? Rise time is the time where a digital signal goes from 10% of the final value to 90% of the final value. Okay, so the time that it takes between 10% to 90%, basically, so that much time is your rise time. Okay, and the fall time is just opposite, the time it takes from 90% of the final value. So this is the final value, so 90% to 10%. I think you must be remembering this definition. So if you simply look at this green curve, so the green curve is the output voltage, which is at the node between these two drains, and the blue is the ideal input, or basically the whatever input, simulated input voltage, not ideal. Now, by just looking at this green curve, look at the slope differences. First of all, this part, the rise part, is not a straight line. It is rather a curvy kind of line with certain slope at every instances. So its slope is not constant everywhere. Same thing over here. This is another falling kind of line where the voltage is falling from logic 1 to 0, whatever, 1.8 to 0 volt. But again, it looks slightly different. If you just look at the waveforms visually, you can see the rise and fall are more or less matched, but not exactly matched, right? In my eyes, I get to see rise is faster and fall is relatively slower. So by looking at this view spice log or error log, you can find the rise is 4.2 into 10 raised to power minus 5 seconds, and then TF is 7.24 into 10 raised to power minus 5. Okay, so now I will stop the simulation. I'll change the width. So let's remember the value. So I'll make it 10 for the PMOS. Okay, so NMOS again 2 and 180. For PMOS, it is 10 and 180. Okay, 10 means the first digit represent width and second digit L in my statement. Okay, so if you run the simulation, again click at output and input. If you look at it, your rise has become faster. Okay, so rise time is actually become smaller, in fact. And just by looking at it, we get to see this kind of information, right? And the fall time, again, it remains the same, because we haven't changed why the fall time doesn't change, because the fall time depends on the lower transistor, which is NMOS, and the rise time depends on the upper transistor, which is PMOS. So why rise time is dependent on upper transistor? Because the current through which the output load capacitance is getting charged depends on the voltage, basically, which is VDD, and the voltage, and there is a resistance R on during the on state, basically, while the MOSFET is on. So we call it R on of a MOSFET. So that R on which is actually charging this capacitance. So this R on multiplied by the load capacitance value represents a time constant. So that is a charging time constant. So charging means from where it is rising, basically, while the voltage is rising at the output, because this output green waveform is the voltage across the capacitor with respect to ground. Now, while increasing the width of the PMOS transistor, what we are doing essentially, we are reducing R. Okay, so but we haven't touched the NMOS, it is as it is. So the fall time remains the same. So fall time remains the same because while the capacitor discharges while the lower transistor is on, at that time the capacitor discharges through NMOS, and while NMOS is discharges, and then NMOS is also offering another add-on. So that add-on into load capacitance is forming the discharging time constant. Okay, so for while the falling action is happening. But from the previous case, 4 micron to 10 micron, I've just increased the width. That means I've widened the size of the, or basically increased the width of the transistor, PMOS transistor. So as a result, R1 decreased. Okay, so now I will again view the log. If you look at the log, basically, then look at this, TR becomes 2.66 into 10 raised to the power minus 5, and the TF remains the same as the previous one. Okay, so from 4, basically, 4 into 10 raised to minus 5, we came to 2 into 10 raised to power minus 5. So we have reduced. So likewise, if you keep on increasing the width of your transistor to, let's say, 20 micron, even wider transistor. So run the simulation, look at the plot. It has become sharper and sharper, right? So the output, this one is sharper and sharper. And if you give an even sharper input, that means the blues lines fall time is even more abrupt. In that case, this will possibly become slightly higher slope will be observed. So what we get to see, the rise time is different, and it depends on the width of the PMOS. So we are only playing with this side, basically, where the green curve is going from 0 to logic 1. So the question, now I can go to another extreme where I'm right clicking on this and then make it only 2 micron. So that means width of the PMOS is same as the width of NMOS. Okay, so both are 2 microns. In that case, basically I can run the simulation. Look at this. So your rise time is actually slower. In fact, it looks like slower, but if you view the log, it looks something strange. So visually, in my eyes, I get to see this is actually slower as compared to this one. But here in the automatic measurement, it looks the same. Now I have basically we have to see where actually these time points exist. So point 0.0058. So wherever is that point with respect to this one. So now the point is this value whatever it is taking as a rise time. So it is actually considering somewhere over here. So at startup, so there are initial startup condition, right? So there's the initial condition. So before startup, we can assume that the system is actually in equilibrium state and basically, and it is not initialized. Basically, all nodes are not initialized. So at that time, so the rise time that this software automatically measures may not be so reliable. So my answer to this question, he has asked in the subsequent question that uh, he has another doubt. So while we change from W2 equal to 2 micro to W1 equal to 2 micro versus W2 equal to 10 and W1 equal to 2. So why the fall times are actually doesn't change much? Okay, so why? And sometimes it is showing the same. So in fact it is not the same. If visually you can see that the rise time is slower, and you should consider not somewhere over here next to time t equal to 0 millisecond and just afterwards. Rather, you should consider the rise time. You can manually measure from 10%, wherever is the 10%, 1.8 volt to this sorry 0.18 volt, which is 10%, and 0.18 minus basically 1.8 minus 0.18, whatever the value. So that point of whatever time you have to note at this point, and you have to note the time at this point, which is 10% and 90% respectively, and then you can minus that and then find that rise time, exact rise time. So what I'm trying to say is that the software doesn't always give you the correct result unless you set the parameters where it is doing the measurement of rise time and fall time.
Excuse me, sir.
Yeah, tell me.
Sir, in this experiment only, I had earlier tried to measure the rise and fall times in between, like not at the end or not at the beginning. But then
Mhm.
also, like the rise time was increasing on increasing the W value. So I'm not sure if it's a fault of the LT spice or something else.
So if you increase the value of W for this upper transistor, which is PMOS, your
Yes,
rise
sir.
time will definitely reduce. Okay,
Yes, sir. It should reduce.
and yeah, it must reduce. And why it must reduce, so that is given. I had shared one file with you, I think, or maybe I've informed you over email. So you have to look at this document where you can calculate the value of R on. So I get to see an equation of R on from this particular document, although it is old, but the theory doesn't actually, some basics doesn't change even if the size and all those parameters change. So R1 is equal to 1 upon mu n Cox W by L into VCC minus V in minus VT. So VT is threshold, V in is input voltage, VCC is the supply voltage, length, width of the transistor, and oxide capacitance in the gate area, and then mobility for the n-channel carrier, which is electron. So by using this equation, if you increase W, then your R1 should decrease, right? And vice versa, because it is 1 upon W. So it is inversely proportional. So increased W means decreased R1 and vice versa. And there are other documents also I can you can find through internet. So there are tutorials on analog switches and multiplexers, although we are not doing analog switches as such, but you can see this curve. So if you plot between the signal voltage versus R on, then look at the curves for NMOS and PMOS. So they are actually different. So this intersection should be ideally somewhere on the y-axis over here, but it is more aligned or basically shifted towards left. So that is the problem. So while you use it as a CMOS inverter, such as this circuit that you are simulating, so we get a combined transfer function as this one. Okay, so combined transfer function as basically this kind of thing for on so for this is basically for the transmission switch, or basically of a CMOS also similar thing is happening, because in Thevenin's equivalent mode VSS and VDD are short. Okay, and that means the resistance between this point and this point, between the source and drain, so they are both parallel to each other, basically, you can think. And in that case, your combined transfer function actually with respect to not basically with just while plotting R1 versus signal voltage is something like moon like partial arc like shape for CMOS. So if you go for only NMOS logic, so this there will be little shift, and also PMOS logic. By even you adjust the sizing, so there is a basically unmatched R1 characteristics over signal voltage. So CMOS, by using the sizing and so on, so you can gradually try to adjust the middle of this curvy portion on the y-axis. That is the ultimate aim. Obviously, that exact signal voltage cannot be maintained all the time. So the problem is, so ideally we want a flat, straight line, horizontal line, okay, which is not so high in R1. So ideally, while the transistor is on, fully in saturation region, so we need, we expect the R1 to be as small as possible, but there is a limit because there is a channel and carriers, so it offers some resistance, finite resistance, but let that finite resistance be very small, and you can make it smaller and smaller by increasing width. And also you should want that this line to be exactly flat, okay, the straight line, vertical horizontal straight line, which should be very close to the this x-axis. But ideally we don't get that. The signal voltage can change, sometimes plus voltage, sometimes minus voltage, sometimes zero, depends on which logic you are using or which analog circuit you are using. So based on that, so the CMOS gives a much better characteristics as compared to R1 characteristics as compared to only NMOS and PMOS. Okay, so this is the reason why you get basically this R1 or the rise time and fall time different, and also how do you adjust that and how do you measure that. So you have to do all take into consideration all these facts. Now in this thing, if I have so far I haven't changed the width of this one, right, the NMOS side, so which is the fall side of the signal. So if I change the width, let's say just arbitrarily choosing some value. Look at this. So it looks like it's almost okay. I can choose even larger width for NMOS. Okay, so by adjusting the width, if you need a symmetric rise and fall, in that case, you have to play around with the width of the MOSFET.
Sir, okay, is it wrong to explain it in terms of current time?
Current, yeah, obviously. So basically, it's a time constant, right? So based on the time constant, so you can use the capacitor charging and discharging equations. Okay, the final voltage and the initial voltage equation. So basically, the charging and discharging equations of the capacitor can be directly applied over here for this first order equivalent system. So you are considering our system is a first order. So there is no other parasitic capacitance, which is not true. Inside MOSFETs, there are lots of parasitic capacitance. Also, for all these connections, external connections, they are all parasitic coupling. Even input and output is having one parasitic capacitance. So assuming all those parasitics are absent, so this waveform is true. And in practice, you'll see there is a slight overshoot here and there is a slight undershoot here in practice. If you measure with oscilloscope, you'll find those overshoot undershoots. And those overshoot undershoot signals, that means it goes beyond a 1.8. So there is nothing more than 1.8 in this circuit. But during measurement under equilibrium or steady state, you will find that this is going slightly above 1.8 and it's coming slightly below 0. So from where that negative and those more than 1.8 voltages are coming. So that happens due to superposition of charge due to those practical stray capacitance or parasitic capacitances, which are unavoidable. You must have, get those capacitances in a MOSFET circuit, and also not just within MOSFET but also at a global level, so while doing all these connections. Is it answered, or you are asking something else?
No, sir, it is answered. Thank you.
Okay, good. Okay, so I'll stop this. Let's see. Okay, so now I request Parth to start with the common source amplifier. Active
Excuse me, sir.
load.
Like,
Do you
just
want
to
me to
start,
share?
clarify one doubt.
Yes, sir.
Yeah, doubt. Yeah.
Yeah, sir. In the previous experiment, like the KP value used was around 0.04 for the NMOS model, and for that the gain was like 18 dB or something like that. But like if you use like in like other in like previous models like model files, then the KP value for that for those models is naturally not that high. So we are getting low values of gain. So do we use your KP values, or do we include, or do we like use like other like inbuilt
Oh,
models?
okay, so you can use either of those two actually. So in this lab experiment, I am not keeping any restriction. In practical cases, we use PDKs, which is process development kits supplied by the manufacturer or the fabricators. Okay, so like TSMC and other companies who fabricate, so they provide the values of KP in their model file. So whatever the model file is saying, you can adopt that, or you can select anything of your own. And obviously, the gain will change and other parameters will change based on your selection of KP, mu n, Cox, and other parameters. So I will give you full marks for that. No problem.
Okay, sir. Thank you.
Okay, Parth, I'm sharing your video. Let's see if this is the video.
Yes, sir.
I'll run the video, and Parth, you can keep on tell me when to stop, and then you
Yes,
can
sir.
explain.
Okay, sir. Fine.
Okay.
Uh, sir, 1 second, sir.
Yeah.
Sir, I sent you another video yesterday. Have you checked that?
Yeah. Yesterday, let me. Oh, yesterday you have sent another video.
Yes, sir.
Just a
That's why I
minute.
was. I can explain this also, but sir, there are a few points I missed in this video that I covered in that
Yeah,
video.
exactly. I saw. I checked this video. Maybe I missed it. Let me check. This one.
Yes, sir. Yesterday only I sent you. Yes. No, sir. I think these are the. Yesterday around 6-7 p.m. in the evening, I sent you the video.
Maybe I have not received because my mailbox is almost full, so I have to clean it
Yes,
up.
sir. That's why I mailed you today about the same thing.
Okay, so I need to clean up. I'm not finding time. So, anyways, what to do? So, do you want to proceed with the older video, and
Yes, sir.
then later I
I
give
can
you the.
proceed, but sir, if you can share the new video with the students, so I have mentioned few more points in that video. That's why.
Okay, so why don't you orally mention those points in this video
Yes,
along with the old video, and
yes.
afterward I'll clean up my mailbox. You send me the video that you were
Okay,
trying to send yesterday. I'll upload that for the students.
okay, sir. Fine.
Okay.
Yes, sir.
Yeah.
So this is the typical circuit for common source amplifier with active load. So what is an active load? You can see in this circuit, I have you in previous circuit we were using a resistive load for the amplifier.
Okay. So you can also explain why you have ignored the biasing and how you are actually compensating by using this thing. So, Parth, you can say that why you are able to replace this and how you are going to adjust the parameter. Some introduction. Can you hear me?
Yes. Hello.
Yeah. So I was unable to hear you.
Sir, I was muted by someone, I think.
Let me check the
No, sir, now
settings.
I.
Okay, you can introduce the circuit.
I was introducing, but someone muted me, I think. Okay,
Oh,
so
let
in
me
this,
check. Okay, but just a moment. I will check the permissions. Just a moment. I'm setting the permissions. Uh, just a moment. Still. Um, hmm, okay. Okay. But can you speak up a little bit?
yes,
Yeah.
yes, sir.
Can you see the screen?
Yes, sir. Thank you.
Okay. Yeah.
I will start.
Yeah.
So this is a common source amplifier with active load. So instead of the resistive load in the previous circuit, we are using an active load in the circuit. Active load is basically a current source. In this case, I am using a PMOS in saturation. Otherwise, you can use a current mirror also. So this will act as a load for this amplifier. See, I have biased this PMOS and saturation region, but if you do the AC equivalent circuit, you will find that gate and source both are shorted. So gate to source connected MOSFET will work as a load in AC equivalent circuit, and equivalent resistance will be RDS, small RDS. Okay, so this is the load for my circuit. One thing we need to keep in mind that see, I have not uh, change the values for Kp or Vth for this parameter, which default values are there. So you can see the VGS value for NMOS and VSG value for PMOS both are same. So if when you make a circuit using this active load, just remember that the current through the NMOS and PMOS should be same. Otherwise, see the NMOS and PMOS both should be in saturation region of operation. So if you fluctuate with the values, you have to calculate the see the source and gate VSG value for PMOS for the same saturation current. Otherwise, your gain will reduce drastically. So this is, sir, I think this is fine. I have given the same VSG and VGS value for the circuit, and further you will see the characteristics of source. Yes, sir.
Okay. You can say now.
Yes, sir. So I've set the DC offset as 0.65, which is VGS for this circuit, VGS for the MOSFET. The amplitude is I've given similarly like 1 millivolt, like the previous circuit, and the frequency I've taken is 1 kilohertz. This is the source. And first we will go for the transient analysis and then the AC analysis.
Okay. So you can explain slightly why you have chosen DC offset voltage for
Yes, sir.
biasing.
Because we need to first we need to operate the transistor in saturation region of operation, right? If I don't choose a DC value, so the AC amplitude, there is a threshold value for this NMOS, right? So if there is no DC offset, the transistor will never go into the saturation region. It will be in offset off region only.
Okay.
DC offset is typically the VGS value for the transistor. Yes, this stopped.
Yeah. Say.
Yes, so this is the output for the circuit. You can see that there is the amplitude, input amplitude was 1 millivolt sine wave. The output is varying from some 0.7 volt to 1.1 volt. I've checked it. And so the gain is high, quite high gain, and the 180-degree out of phase, which was required. We know that for common source amplifier, the output is 180-degree out of phase for input. Right. So yeah, this is the simple transient analysis for the circuit. Yes, sir. Fine.
Yeah, you can say.
Yes, sir. This is the input for the circuit, and before that you saw the output. You can see the input is varying from 650.1 millivolt and like 649. So the input amplitude is very less compared to the output amplitude. And I think further you can see both of them together in this video. But sir, I think the point is clear. We can go forward, and when you share the video, these things are mentioned clearly in that.
Yeah.
Someone, yes, sir. Someone asked that can we change that AC amplitude from 1 to 1 milli or anything we want? But sir, I have checked that if we change that AC amplitude, then the gain is getting affected. So there is I think we need to change the output command for that. So right now I have done with AC amplitude 1 only, and further we can check. But the amplitude is getting gain is getting reduced if we change the AC amplitude here.
So there might be some issues with LT Spice also, because LT Spice is not a very professional and accurate software. It is usually it's easy to use but lightweight software. So Cadence will tell you the final answer to this question.
So if you want to check like this only, you can use AC amplitude as 1. You can change other values if you want to check other things. Yes, I've just changed the source. Yeah. DC offset should be there to maintain that. Yeah, this is for AC analysis. I've changed. I think you all remember the previous video, almost same setting. Just you had to fix the start and stop frequency and points per decade.
Yeah, you can say now.
Yes, just need to click on that output. You can see there's a quite high gain, but the bandwidth is quite low, not very high bandwidth for the circuit. So this is like this was a this circuit needs some improvement to get the high bandwidth. This in this video, I think I have not done that, but the video you will get the video where sir will share with you. You can see the other things which you can make other things to get the high bandwidth. You can do other things. Okay. So this circuit, similarly like the previous video, you can calculate the 3 dB frequency for this amplifier. You can say that there is no lower cutoff because in the previous circuit there was a blocking capacitor at input end. In this circuit, I have not used that. Because of that, there was a lower cutoff also, 3 dB cutoff also. But in the circuit, there is no lower 3 dB cutoff. Only at when you increase the frequency higher, you will get a 3 dB 3 dB frequency. Okay. Thank you. In a similar way, I have calculated the 3 dB frequency here also, just like the previous video.
Here. You can explain that?
Yes, sir. The 3 dB frequency is similar. The frequency at which the gain reduced to 3 dB by your maximum value, maximum gain value. And just by clicking on this, like say VN003, you can get this window, and you can move the cursor along and get the frequency and magnitude at that point. Okay. One thing which is not mentioned in this video is what is the advantage of using active load over resistive load. So first you know that that resistors, they take a high area. So if you use the resistor first, they will consume more area. And secondly, if you use a resistor, there will be a drop across that resistor. So your output voltage swing will reduce. So you get a LED. So if we are using a resistor at output, there will be a drop across this resistor. So the output voltage swing, it will get reduced and it will get affected because of the resistor. So these are the two advantages. And I think, sir, if you can mention some more advantages, but I can think of these two only.
Yeah, so you're right actually. So space is the main advantage for using the active load. Basically, the upper resistor is replaced by a transistor, and also if you need a programmable gain, for example, if you look at the schematic. Yeah, so if you need a programmable gain, in that case, you can change this biasing voltage, or if you need a fixed gain, just set the WA by L of the PMOS transistor and put it in a diode connected mode. In diode connected means the gate is connected to drain, okay, for PMOS. So this either diode connected mode will give you fixed resistance or fixed equivalent resistance, but fixed gain, that will give you fixed gain. But in addition, if you need a programmable gain, you can apply a different biasing voltages. So based on the biasing voltages, your R on of this particular MOSFET, the upper MOSFET, can be different. So that means you can adjust the resistance. So that means you can adjust the gain of your amplifier, because gain of this kind of amplifier, or common source amplifier, is minus GM into RD. So that is the simplest equation. So GM is the transconductance over here, and RD is the drain resistance. So instead of drain resistance, the R on of this PMOS is your RD. Now, in terms of voltage drop, I think part you were slightly wrong, because voltage drop, so whatever is the RD or in simple fixed resistor, voltage drop will always be there. Okay, so voltage drop is always there, and if there is a voltage drop, so it's a KVL loop. So this V2, whatever voltage for V2, which is VDD actually. So VDD minus ID into RD is the voltage drop. Okay, now whatever instead of RD, this is R on of a PMOS. So again, there will be voltage drops. There is no escape from that. But only thing is that in terms of size, there is a huge advantage because it is much smaller in size. In terms of programmability, by changing the gate voltage, basically gate to source voltage, that's another huge advantage. So you can make a programmable gain amplifier very easily by using active load circuit for common source amplifier. And again, so in terms of matches, so there is another point. which is the temperature coefficient, because if you use a simple resistor, so if you fabricate on-chip resistor, that will take a lot of space. That is one thing. But if this, apart from that, the resistor material, if you use a fixed resistor, whether on-chip or off-chip, that will have a different temperature coefficient. Okay, so typically those resistors are made of carbon film or some sort of metal film. So rarely with basically, if it is a semiconductor chip-based resistor, then it's with some doping concentration difference in the silicon area. But the point is, the temperature coefficient is the main issue, another important issue, because if there is an increase in temperature, the value of resistance change for this resistor will be different than the value of the parameter change, which is R1 of the lower transistor, will be different. So as a result, so your gain is subject to ambient temperature. Whereas if you use a MOSFET, then they are on the same substrate, similar basically material concentration, approximately similar material. So that is why if temperature increases or decreases, so it's a ratiometric device. So the ratio of the upper resistance and the lower resistance actually gets cancelled out. So overall, the gain doesn't have that very large drift due to change in ambient temperature. So these are other advantages. Okay, so we'll yeah, yeah. So, Parth, did you cover any other point in your second view?
No, sir. These are the points. One thing, sir, I changed these values, WL values for the in that video. So
Okay.
there is the drop. The gain in that is typically 42 dBs, something like that. And if I change the WL values, the reason of operation was just for this transistor was changed. So the gain was dropped drastically in that video. You can see that in that video. I think the reason was the reason of operation was changing for the transistors.
So, from which region to what region? So, you are operating at saturation here. So,
Yes.
was that a triode operation?
Yes, sir. That was checked. So at a PMOS, if sir, it depends on what value you are changing. So maybe the PMOS was changing to triode region, and that's why the equivalent resistance was dropping. So the gain was dropped by a large value, I think.
Okay. So the point basically what Parth is saying, that you have to keep track of the region of operation. So for common source amplifier, your lower resistor, lower transistor, basically the NMOS must always be in saturation. But the PMOS, you have flexibility. You can keep it either saturation, preferably in saturation. But triode is also possible. But with triode, if there is supply voltage variation, then you might get in different Q point. Okay, so this is the meaning that if you keep the upper, preferably you should keep M2 in saturation mode. But in case if it is in triode due to your adjusted voltage over here, then it will still work as a resistor. But the point is, if there is slight variation in supply voltage, let's say you are using a battery of 3 volt, and from there you are using 1.8 after voltage regulator. So if your voltage regulator fails, or if you have some change in the voltage output, I mean power supply voltage, due to whatever reason, there could be noise also. In such case, the R on of this upper transistor is going to change, and if R1 changes, obviously your gain will fluctuate. So that means with power supply, your gain will fluctuate if you keep it in triode region. So preferably you keep it in saturation, and lower one must always be in saturation mode. Okay. Any question from this circuit? So you have to do transient simulation as well as AC simulation. Look at another point over here. So at startup, look at this waveform. So this is not a sine wave. It looks like some noise before the circuit really starts with the sine wave signal. So if you do any measurement at this point, that is going to be ignored. Okay, so you must ignore the initial few millisecond time preferably, and take somewhere from the middle. So you can show 3 or 4 cycles. That itself is good enough. More is also enough, but don't show thousands of cycles over here. So that is also too cluttered. So make sure your sine wave is easily visible, it is readable, and so on. Okay, any question from this common source with active load? Seems no question. Okay, so now Arnab, are you there? Arnab?
Yes, sir.
Okay, so I'll request Arnab to present. I'll give you the permission. You can share the screen and you can start your video.
Okay.
So I'll give you the permission first. Okay, Arnab, I've given you the permission to share the screen. You can start sharing your screen.
Okay.
So Arnab will be discussing about the cadence equivalent design practices for designing common source amplifier, both resistive load as well as active load.
Can you see the video?
Yeah, I can see your screen. Yeah.
Okay. So here we have the two CS amplifier. This is the resistive load one. Another one is the common active load one, diode connected active load. So I'd like to correct one thing here, is that a diode connected MOS is when you connect the gate and drain together, not the gate and source. If you connect the gate and source together, the MOS will be off forever.
Oh, yeah.
Okay. So these are the sources.
It must be gate and drain, obviously. And for the PMOS, the load side terminal is the drain terminal.
Yes. So these are the sources. We have the alias ground, VDD is the supply. We have VG. So this VG will act as a biasing source as well as our AC input source. And this is a sine wave to test the transient characteristics. Now I'll show you what the VG has. The VG has a bias voltage of 600 millivolts. You can get it by a resistor divider circuit, but in case of CMOS, we use separate band gap reference, and from that band gap reference, we use current mirrors to get our desired voltage. So I've used a 600 millivolt bias voltage and an AC magnitude of 1 millivolt. This is used to test the gain and phase of this circuit. This is the sine wave which I have used. So I'll use this is 900. You can ignore. I've used 600 in that case also, and an amplitude of 100 millivolt and sine wave frequency of 100 kilohertz. This is just to test the transient characteristics.
So we are applying this DC offset in order to keep the transistor in saturation.
Transistor is to bias the lower NMOS. So this is the AC window. What we'll do AC analysis. So it's very simple. All you need to give is the frequency range. From what frequency you want to see the gain and phase of the circuit. So I've taken a large range just to show you what the gain and phase will be. So this is to simulate the circuit. You need to press the run button. So we'll check both the Vout and Vout1. Vout is the one with the resistive load, and Vout1 is the one with the active load.
So he's doing check and save. So it's showing some warning, but it's okay.
X. The warning is because the V sign signal is not connected anywhere, right? It is open. So I'll only use it in transient simulation. That's the warning you're getting. Okay, these are the two signals. So this is for the active load. So our input,
Carefully look at the curves. They are quite light in color. Basically, this isn't good color contrast, but it's okay.
So this is one is for that active load. So I had my initial input signal had an AC magnitude of 1 volt, and I'm getting more than 4 volt. And for this resistive load, I'm getting close to 2. In case of CS amplifier in TSMC or any other process, the maximum gain you can get is close around 20 dB. So in order to get higher gain, you have to use an op amp or a telescopic amplifier.
So there are limitations of common source amplifier using single stage. Either you have to use multi-stage format,
or
or
you have to use for op amp based of a kind of 5-pack circuit.
So here Arnav is simulating both resistive load and active load at the same time. So simultaneously, both the circuits are running in the simulation. You can also do the same thing in LT.
Yeah. So in order to see there's a very special feature in Cadence. You can see the gain and phase. So what you need to do is to go to results, direct plot, AC gains and phase. AC gain and phase is this one. Results, direct plot, AC gain phase. So once you go there, what you need to do is click on your output wire and the input wire. So this is my output wire for the resistive one, and the input is my VG. So I'll click on it, and it will give me the gain and phase plot. So this lower one is my gain plot, and this is my phase plot. So you can measure the phase margin, the 3 dB frequency, and everything. So what I'll do, I'll just see the phase drop here. Since this is a single pole system, so the phase drop will not be much more than 90 degrees. You can see there is a phase drop of close to 64 degrees here. So it's in 1 dB. Let me have to drag it down to. Yeah. So once you drag it down to say close to 0 dB, you can see that phase drop is 70 degrees. So in order to get this line, you need to press V on your graph. So once you press V, there will be a vertical line. I'll do the similar thing for the active load. Again, you have to go to results, direct plot, AC gain phase, and click on the output wire, then the input wire. Here also you can click V and see the AC gain and phase. The pole is located closer here because the MOS itself introduces some parasitic gap. So the pole location is closer to the origin. Now, so I'll show some properties like in case of resistive load, I need to use a wide MOS because I cannot use a large resistor, because in MOS we cannot, in CMOS technology we cannot have the resistor occupies a large area. So what we need to do, we need to increase the W, hence the GM will increase. As a result, our gain will be sufficient. So here we have to use a larger width of the MOS, which can be a disadvantage. That's why in most cases, in case of CMOS design, we use diode connected MOS as load. So if you look at this diode connected one, I'm getting a higher gain with a much smaller width of the MOS. So in this case, the gain is given by GM of the lower NMOS divided by GM of the PMOS. So this PMOS, if you look in terms of AC resistance, its resistance is 1 by GM. So my overall gain is GMN by GMP. Now if I increase the width of this one, my GM will increase, hence my gain will increase. So I need to keep this at a minimum width. Also, I have to consider the drop across this also. Hence, as the drop should not be more, otherwise the Q point will come down to a lower level. I will show you the current consumption in separately. So next, what we'll do, I'll just see the transient characteristics. So I'll just remove this VG and use V sign. So the V sign, the sinusoidal signal with a DC bias. Okay. Let's check and save this and run the simulation. So you can see the three signals together, V out 1, V out, and now my V sign is the input signal. So if you look at it, so I had given an amplitude of 100 millivolts, so the peak to peak will be 200.
Waves, yeah, Arnav, the waves are so lightly shown. So please take your cursor and show them clearly.
Okay, so this is the V sign one. Okay, just hold on. I'll just go to the this thing. If I can go, I'll just go to the remote access. If I can.
Oh,
Can you see this is the remote access?
Yeah, you can try.
Yeah, so I am in the remote window. So this is the peak to peak, and here I'm using 50 millivolts just to show you. The peak to peak is 100. In this case, the peak to peak is close to 200. So this is the input. Peak to peak is 100, and this is the peak to peak is 200, and this is for the diode connected MOS. And this current. So just wait a minute. So just to show you the current consumption, I have clicked on this node. So the total current consumption for the active case. So I'm just burning. You can see average current of only 40 microwatts to get a gain of 4 times. Just 40 microampere I'm just burning. And these are the gains. This is my input signal. And this is my active load output. This is the resistive load output. So if you have any doubt, I have the screen ready with me. I can run other change some parameters and show you.
Questions?
Can you go back to the graph?
Sorry?
Can you go back to the graph for a second, like the 4 graphs?
Yeah, sure. This one. Yeah, this one, right?
Yeah. So the top one is
The top one is for the resistive one. So this one is my input signal. This one is my output for the resistive one. See, there will be a DC bias because it will be on top of a DC signal in between the resistor and the MOS. You just need to check the peak to peak. Yeah, what was your doubt?
And the lower two signals are like
This is for the active load output, and this one I'm just showing you the current. So the current across this transistor. I'm just showing you for the sake of showing you that if you use an active diode, you can design an amplifier with a very low amount of current consumption.
and it's like deviating from the sign characteristics, the V also, right? The output, the white plot. So
This
it
one,
is
yeah,
like
this is
too much input, basically, right?
sorry.
The input is too high, and therefore it is going out
Yeah,
of
that
the.
is, if you reduce the input amplitude, it will give you a proper signal, or you can just change the cue point, just adjust the sizing of these two so that this is at 0.9 volt, midpoint of 1.8 and 0. So then you can have that maximum high swing. Yeah, the compliance will be higher.
Arnab, possibly your NMOS is going out of saturation. That's why you're getting those kind of flattish thing on the bottom side of white.
Yeah, maybe. So,
or you can add an offset to the input or reduce the input voltage.
Yeah, I can try that. Just hold on.
So there are different ways to combat such problems. So either you have to add some offset voltage along with the sine wave, such that it stays always in the active region. So the cue point should never leave that saturation region, I mean. Or change the sizing also will do the same thing, because transconductance will be changed. So as a result, gain will be changed.
Yeah, see now just I just changed the bias current, the sine wave output is now properly sinusoidal output. You can see there is a phase difference, right, between the input and the output. So I just made the bias, the DC voltage from 600 millivolt to 520 millivolt.
Yeah, so this is how actually we do optimize our circuits to make sure that it will work correctly in real scenario.
So,
and Arnab, can you please explain why the current is also sine wave like?
Current is?
Yeah, current is also somewhat following the sine wave.
No, so there is a DC current and there is an AC signal to it. So when the signal, this voltage is rising, the current is controlled by this NMOS, right? This acts as a resistor. This does not control any current. So when the input signal rises at this node, the current will increase. When the input signal falls, the current will decrease. That's what is happening. So there is a see, if you look at it, there is an static. There is 8 microamp. On top of it, there is a second sign. So if you do a DC analysis, it will give you only close to 10 micro kind of thing.
Yeah, good.
So since we do not use resistors in CMOS, so as sir had told that we use some band gap something for biasing. So sir, for our simulations also we should not use any resistors, and wherever biasing is applied, we apply voltage source.
No, in case of biasing, you are using a voltage source. We are using only voltage source. We are not using any reference. The reference itself is a circuit.
No, sir.
Arnab, this question is about PMOS actually. So can
PMOS,
we use a voltage source? That what we
see there's two ways. You can either give a bias voltage to this PMOS and bias this branch. If you bias any of this, the branch will have the same current, right? The current is flowing from this node to the ground. Now I can either bias this PMOS or you can bias this NMOS. But when you bias this PMOS, you have to use just a DC voltage. Your sinusoidal will be here. Otherwise, if you are doing a CS amplifier with load as NMOS and input as PMOS, what you will do, you'll connect this from this gate and drain. This will act as your load, and you'll apply your bias and your signal at the PMOS. So is it clear? You can have CS amplifier both ways. You can have the input as the NMOS as well as the PMOS, and the other one will act as your load.
Yes, sir. So that was fine. Sir, I wanted to ask for simulations that we would do now or for future. So, sir, we, as you have done to use a voltage for
Yeah, for
input,
now,
we
for this, yeah, you can use a voltage source for simulation purpose for this course.
yes, sir.
Sir?
Yeah.
Sir, in this, is there any way, means, is the lambda parameter already set, or we have the ability to set it as well?
No, you don't have any. You have the control over width, length, and the biasing voltage. The rest of it is set by the foundry.
Okay, so there are two ways to look at your question. So lambda, there is something with layout. There is a lambda rule, and there is a lambda channel length modulation parameter lambda. Okay, so which lambda are you talking about?
Okay.
So the channel length one.
Okay, so the channel length modulation parameter is already taken care in the model file in the background, because this is TSMC 180 nanometer PDK. So this is much more formal model, which is available and much more accurate also, which is already loaded in the background for cadence simulation.
Sir, and also while you were plotting the gain dB versus phase and all, there was an option to plot magnitude dB and phase as well. So what's the difference between them?
I'll be back in some time.
Yeah, so gain is your V out by V in. Okay, so it's 20 log V out by V in. Gain dB, and I think magnitude dB, you don't have a magnitude dB. dB is I think it's a ratio, right? You cannot have a single term to denote a decibel function. You can either have a power dB, power out by power in, 10 log V out by P in, or 20 log V out by V in. Is it clear?
Yes, sir.
dB itself is a ratio, denotes a ratio between two voltage. Is there any other question?
So any other question? Okay. Arnab, please look at the chat box. Someone is asking whether the input waveforms are the same or not. So I think it was same, right?
Yeah, the input signal is same for both ones.
Sir, it's a very old question.
Oh,
So
old
last
question.
week's.
Oh, it's last week question. Oh, sorry. I thought it's today's question. Okay. Oh, that's 18.1. Yeah. Okay, any other question about common source amplifiers? So again, cadence part, we'll ask you through Viva or some sort of other theoretical question, whatever we'll be covering based on that only. So you have to, I'll upload both the videos today, and then you have to study, and then you have to repeat the LT Spice side, but cadence side, you just have to watch it and understand. Okay, in the next week, by next week, you have to upload the common source amplifier, both the side parts, and then you have to, next week we'll cover op-amp, and also we'll see if layout time remains, we'll consider layout as well. Otherwise, we'll consider layout as next week. So essentially, we have 2 more class slots next week and the week afterwards for analog, and then analog classes will stop. Then the third week from now, Professor Vivek Dikshit will start on the digital side. Okay, so on analog, as you know, there are 4 experiments. You have to fulfill the requirements for the full assignment submissions, and we will see what else will be the marking point. As I said, the quiz will be one, Viva could be one. So we had yet to decide that. Okay, so any other question regarding submission or any other previous experiment?
Tomorrow we have to submit common source amplifier with resistive load, right?
Yes.
Okay, thank you.
And for experiment 1, yeah, tell me.
Sir, is it okay if I can ask doubts on first experiment now?
Yes, sure.
Sir, actually, you showed the simulation file regarding, you told that we shouldn't measure at the initial states because there is a transition which we may not be knowing the initial conditions. So I later changed the delay factor as well. But in still some cases, when I change only the width of PMOS, my fall time is also decreasing or increasing. And in some cases, if we increase width, the rise time is also increasing.
So that may be due to some extra capacitance, because once you increase the width of a transistor, it also adds to the parasitics inside the transistor. So maybe the model that you are using or the accuracy of the model matters. Maybe for that reason you are getting such weird result. So
both
which model are you using? That 180 nanometer? Default one, okay. So that is okay, but it may not be very accurate, because as I said, in professional PDKs, as you have seen in Cadence, the people fabricate the MOSFETs, they get those values verified over several hundred runs or thousands of runs. Okay, so they fabricate multiple MOSFETs and they keep on checking whether the parameters are matching or not, like K, mu, N, Cox, and other parameters. Okay, so that's why the PDKs are much more accurate as compared to simplistic models. Yeah, but it is okay for now. It's not necessary that you must be very, very accurate with LT Spice.
And so in the previous experiment, we have with RL capacitor CSH, which has been set to 10 picofarad. If you increase it to a few nanofarads, you obviously see a shift, as in like a delay. And then you also observe that that the gain has fallen. So like I was reasoning, that is it because like if you have a very large capacitor, the amplifier will not be able to charge it and discharge it in time, or is that and if you increase it, obviously if you increase it to 1 microfarad or something like that, then it the gain becomes like negative, so the output waveform is actually smaller than the input waveform. So like, is that the reason, because of you can't charge the capacitor, or is it?
That's one of the reasons. Definitely, that's the dominating factor. Because if you have a large capacitance, you need large wide MOSFETs also to charge that up. So, for given the size W by L for both upper or lower MOSFETs or any one of the MOSFETs. So it will have only finite amount of resistance while it is in saturation mode. So that resistance into capacitance is again coming down to the original point that I was making earlier today, the time constant. So obviously, if you have a large capacitance like nano or micro, so the transistor may not be able to charge up fully. And from this fact, while studying op-amp, you must have come across slew rate. So the slew rate is the maximum rate of change in voltage. At the output of an op-amp. So the slew rate, obviously that slew rate term is used in terms of op-amp, but it actually came from the drive signal driving ability, basically what is the output current driving ability or sinking ability or sourcing ability of a transistorized stage, and the corresponding capacitance of the pin and the connections. So if the capacitance is very large, your slew rate is going to be smaller, and vice versa, right, for a given sizing of a transistor. So obviously, you have to make an optimal choice. So what should be the range of capacitance that is acceptable as a load, and also what should be the width and length of the transistor. Length, obviously, we cannot change for a given technology, but width we can play around.
The other reason is if you look at the AC small signal model, the resistor and the capacitor, they come in parallel. If you increase the size of the capacitor, the overall load resistance drops. So that is another reason why the gain drops. So it's 1 by omega c, right? If you increase c, so that 1 by omega c, the xc term drops, and the R is in parallel with the capacitor if you draw the small signal model. So the overall load resistance drops. So if your load resistance drops, your gain will automatically drop.
Yeah, and also it depends on frequency of operation.
Yeah.
So the omega term.
Yeah, that's why its bandwidth is also very less. It's only about 6
because the pole is RC, the combination of R and C. So the pole will be closer to the origin.
Yeah, that makes a lot of sense. Yeah, thank you.
Any other question? Okay, if you don't have any questions, so we'll stop the class over here itself. So please prepare yourself for the submission tomorrow for the common source amplifier with resistive load. Okay, so I'll note down attendance for students. I'll stop recording.